Welcome to the fascinating world of chemical bonding. Have you ever wondered how molecules like methane or ammonia take such specific shapes? Well, the secret lies in something called hybridization, a concept that helps us understand how atoms bond and form stable molecules. Imagine two atoms coming together to form a molecule. They don't just connect randomly, they do so in a very specific way, creating bonds that shape the very molecule itself. Hybridization is when atomic orbitals mix together to form new orbitals with equivalent energies and shapes. These new hybrid orbitals play a crucial role in bond formation, allowing atoms to achieve a stable configuration. The number of hybrid orbitals formed is equal to the number of atomic orbitals that combine. The way these orbitals arrange themselves in space is what gives a molecule its shape and its unique properties. Now, how does this tie into the chemistry we observe around us? When you think of water or methane, you're actually looking at molecules where hybridization explains their bond angles and three-dimensional structure. So, let's dive in and explore how atoms reshape their orbitals for bond formation. Let's look at the different types of hybridization that shape the molecules we see every day. The first type we'll explore is sp hybridization. This happens when one s orbital and one p orbital combine, resulting in two sp hybrid orbitals. These orbitals point in exactly opposite directions, creating a straight line, hence, a linear molecule. This type of hybridization forms molecules like beryllium chloride, where the bond angle is a perfect 180 degrees. Next, we have sp superscript 2 hybridization. In this case, one s orbital and two p orbitals combine to form three sp superscript 2 hybrid orbitals. These orbitals align in a trigonal planar arrangement, meaning they form a flat, triangle-like shape with bond angles of 120 degrees. A perfect example is boron trichloride, where this geometry helps the boron atom form stable bonds with chlorine atoms. Finally, we have sp superscript 3 hybridization, which involves one s orbital and three p orbitals coming together to form four sp superscript 3 hybrid orbitals. These orbitals align themselves in a tetrahedral shape with bond angles of 109.5 degrees as seen in methane. This geometry allows the molecule to be stable with a 3D structure perfectly suited to its needs. Let's take a closer look at sp hybridization and its impact on molecular geometry. In sp hybridization, we see this in molecules like beryllium chloride. The central beryllium atom undergoes hybridization, mixing one s orbital with one p orbital to form two sp hybrid orbitals. These two orbitals align in opposite directions, creating a straight line. The result is a linear geometry with a bond angle of 180 degrees. The sp orbitals of beryllium overlap axially with chlorine's 2p orbitals to form two sigma bonds. So, as you can see in the structure of beryllium chloride, this linear geometry is stable due to the effective overlap of the orbitals. The molecule looks like a straight line, simple yet highly efficient. The bond is strong because of the maximum orbital overlap, making this molecule a great example of how hybridization shapes molecular structure. Next, let's explore sp superscript 2 hybridization, which gives rise to trigonal planar molecules. Take the example of boron trichloride. In this molecule, the central boron atom undergoes sp superscript 2 hybridization, mixing one s orbital and two p orbitals. These three hybrid orbitals form a trigonal planar shape where the bond angles are 120 degrees. The remaining unhybridized p orbital forms a pi bond when it overlaps with another p orbital in molecules like ethene. This geometry is essential for the stability of molecules like boron trichloride and ethene. As we'll see, The trigonal planar arrangement helps atoms to stay as far apart as possible, reducing repulsion and leading to stronger bonds. This is why molecules with sp superscript 2 hybridization, like ethene, have the unique ability to form double bonds, which we'll discuss shortly. Not all bonds are ionic. In some molecules, atoms share electrons rather than transferring them. This is known as covalent bonding. Take the hydrogen molecule as an example. Two hydrogen atoms come together and share a pair of electrons. By doing so, each hydrogen atom completes its outer shell, achieving stability. This kind of bond, where electrons are shared, is the essence of covalent bonding. And it's not always just one pair of electrons, sometimes atoms share multiple pairs. For example, in carbon dioxide, each carbon atom shares two pairs of electrons with oxygen, forming double bonds. This sharing of electrons leads to the creation of stable molecules, and it's how we form the world of organic and inorganic compounds. Now, let's look at how hybridization works in real organic molecules. In ethane, both carbon atoms undergo sp superscript 3 hybridization, forming single bonds with hydrogen and with each other. The carbon-carbon CC bond and the carbon-hydrogen CH bonds in ethane are all sigma bonds, and the bond length of CC is 154 picometers, while CH is 109 picometers. This is a great example of how sp superscript 3 hybrid orbitals lead to stable molecules with single bonds. In ethene, we see a different story. Here, each carbon atom undergoes sp superscript 2 hybridization. The carbon-carbon CC bond consists of one sigma bond and one pi bond, with the pi bond formed by the unhybridized p orbitals overlapping sideways. The bond length of CC is 134 picometers, and the hydrogen-carbon-hydrogen HCH bond angle is 117.6 degrees. Ethene's double bond structure allows for unique chemical reactivity, which we'll explore later. Hybridization can also involve d orbitals, especially in third-period elements like phosphorus. In phosphorus pentachloride, the phosphorus atom undergoes sp superscript 3d hybridization, mixing one s orbital, 3 p orbitals, and 1 d orbital to form 5 sp superscript 3d hybrid orbitals. These orbitals arrange in a trigonal bipyramidal geometry, which is essential for the structure of phosphorus pentachloride. Similarly, other molecules like sulfur hexafluoride use sp superscript 3d superscript 2 hybridization to form an octahedral geometry, allowing them to accommodate more bonds and achieve greater stability. To sum up, hybridization is a key concept in chemistry that explains how atoms form bonds and determine the shapes of molecules. From simple molecules like methane, with its tetrahedral geometry, to more complex molecules like phosphorus pentachloride with its trigonal bipyramidal shape, hybridization is at the heart of molecular chemistry. I hope this session helped you see how hybridization is more than just theory. It's the key to understanding everything from organic molecules to complex coordination compounds. See you in the next class, where we'll explore more fascinating chemical concepts.